Welcome to our presentation about using novelty search to explicitly create diversity in ensembles of classifiers. Here we present an innovative algorithm to build behaviorally diverse ensembles for image classification. This algorithm does an explicit search for a set of diverse classifiers using novelty search, rather than relying on implicit methods. And unlike most evolutionary machine learning, the search is guided by behavioral novelty only, not by accuracy. We know that ensemble models are capable of outperforming their individual learners when they are sufficiently diverse, but there is no standard agreement on how diversity should be defined and how to exploit it to construct a high-performing classifier. We propose diversity metrics based on the divergence of errors. Our novelty search algorithm evolved behaviorally diverse neural networks for image classification. Here is an overview of our algorithm. It is a novelty search algorithm. It searches a space of neural network architectures, but novelty is measured in the behavioral space of neural networks. A set of networks is returned from which the final ensemble is selected. The individual architectures are based on wide residual networks. Here is the general architecture of individual neural networks. There is a convolutional layer followed by a number of residual blocks. There is an average pooling layer before the final output is produced. Evolution will operate over the convolutional layer or the residual blocks. Here is the general architecture of a residual block. The input is passed through two convolutional layers, and then the result is added to the input to produce the output. The convolutional layer at the right-hand side is only necessary if the size of the input is different from the size of the output. There is a dropout layer between the two convolutional layers. To guide the novelty search, we have proposed two behavioral diversity metrics, and additionally considered one metric from the literature. The first metric we propose is the error proportion metric, which measures the proportion of instances where two models make different mistakes out of all the instances where at least one of them makes a mistake. The second metric we propose is the cosine distance between the vectors of wrong predictions made by two different models. The disagreement metric, number 3, is found in the literature, and it measures the proportion of instances where two models make different errors out of all instances in the data. In order to choose models to add to the final ensemble, we consider two ensemble selection metrics. The first metric that we consider is the mean behavioral diversity metric. This one we propose ourselves. We select one of the three behavioral diversity metrics from the previous slide, and we calculate its mean value between the model that we're considering and all the current ensemble members. The second metric, which is found in the literature, is the entropy metric. It is calculated for a set of models, so we create candidate ensembles made up of the current ensemble members and each of the candidate models that we are considering. Here is an overview of the novelty search algorithm. We begin by training all the networks in the population with a standard gradient descent procedure. Then, considering all the members in the population and in the archive, we calculate pairwise behavioral diversity metrics. Then we use these to calculate novelty scores. We add a random sample to the archive, and we add the member that scores the highest selection diversity metric to the ensemble. We then use the novelty scores to evolve a new generation by a mutation. All of the diversity metrics are calculated with respect to a validation set. This pairwise distance is one of the behavioral diversity metrics that we saw. The novelty score is calculated with respect to the k nearest neighbors of each model. When selecting models for reproduction, we use tournament selection. Reproduction uses only the mutation operator. This is to preserve diversity. Mutation operates by adding or removing blocks, swapping blocks, changing the size of the first convolutional layer in the network, or changing the size and dropout probability of the residual blocks. We compare the novelty search algorithm with some baseline methods. The first one we call random search. It is basically like the novelty search, but instead of using the novelty scores to evolve a new population at each generation, we simply initialize a new random population at every iteration. The second method is an ensemble that only uses implicit methods for creating diversity, namely architectural diversity, different random initializations, and training the members on different subsets of the data. The third baseline is simply the single best performing model in the ensemble. We have conducted experiments to test 4 hypotheses. The first one states that ensembles will outperform their single best member. The second hypothesis states that novelty search will lead to higher performing ensembles than random search. And the third hypothesis states that novelty search will lead to better ensembles than those created with implicit diversity methods. The last hypothesis states that error diversity metrics, that is, metrics that focus more closely on the errors made by different models, perform better than generic diversity metrics. This table shows the range of hyperparameters that are varied by the evolution in order to create different architectures. You can see by the number of channels of the first convolutional layer and of residual blocks that we only consider small architectures. This table shows the accuracy results for the baseline methods. You can see that the cosine distance metric is the behavioral diversity metric that tends to lead to the better results. You can also see that a random search, which only uses an ensemble selection metric, still tends to outperform methods that only implicitly create diversity. This is the case when the mean behavioral diversity metric is used as the ensemble selection metric. You can also see that ensembles tend to outperform their single best individual. Again, this is true mostly when the ensemble selection metric is the mean behavioral diversity metric. This table shows the accuracy results for the novelty search algorithm and some comparable results from the literature. If we only consider the novelty search results, we see that the error proportion metric tends to lead to better results. We also see that using the mean behavioral diversity metric as the ensemble selection metric works better than using the entropy metric. Again, we observe that ensembles tend to outperform their single best individual. Some of these results from the literature are better than our results. We have included them here because they are comparable to our results, in the sense that they also use shallow networks. But these networks are not the same complexity as ours, and these methods use a lot more fine-tuning than our methods. We point out that in the meantime we have considerably improved on these results shown here. Regarding the first hypothesis, we have observed that ensembles generated with the novelty search algorithm outperform their single best individual. This means that explicitly searching for diversity alone without rewarding accuracy does not impact negatively upon ensemble performance. On the contrary, regarding the second hypothesis, we have found that the novelty search outperforms the random search on the harder problems, CIFAR-10 and CIFAR-100, but not on the easier one, SVHN. The performance gain is largest on the harder problem. This means that searching for diversity explicitly is a good strategy, but a random search might be more appropriate on simpler problem domains. Regarding the third hypothesis, we have observed that both the novelty search and the random search lead to ensembles that outperform those generated with implicit diversity, but only with the metrics that we propose, the error proportion metric and the cosine distance metric, not with the disagreement metric commonly found in the literature. Regarding the last hypothesis, we have observed that the error diversity metrics that we propose, the error proportion metric and the cosine distance metric, lead to better results than the more generic metrics found in the literature, the disagreement metric and the entropy metric. They seem to be more correlated with ensemble accuracy, and thus better suited to the task of searching for diversity. We now analyze briefly the type of architectures that tend to be selected by the novelty search algorithm. For instance, in this figure, we see that the novelty search algorithm tends to select networks with a higher number of residual blocks. This is perhaps unsurprising. We also see that the novelty search tends to select the higher block sizes within the range we are considering. We also observe that smaller dropout values within the residual blocks tend to be selected more often. To summarize the main conclusions, we have proposed a novelty search method to explicitly search for behavioral diversity. This method not simply rewards diversity, but actively searches for it. We also propose 2 new behavioral diversity metrics and a selection metric. The accuracy of the models is ensured by a gradient descent procedure, but it's not an explicit objective of the novelty search. We have concluded that searching for diversity without selecting for accuracy has shown promising results. The novelty search algorithm significantly outperforms a random search baseline which only rewards diversity. It also outperforms a baseline which only makes use of implicit diversity methods. Our error diversity metrics lead to better results than others commonly found in the literature. We believe our research provides valuable insights into the problem of promoting diversity in ensembles of classifiers. It suggests that explicit creation of diversity should be adopted on harder problems that implicit methods struggle to solve, and also that diversity metrics should focus on the errors made by individual learners. Currently, we are extending this novelty search approach with local competition to include accuracy objectives. We are also using surrogate models to avoid the costly step of training models with gradient descent at each iteration of the novelty search. We are looking into new ways to study the trade-off between individual model accuracy and ensemble diversity, and also the trade-off between high-performing but less diverse and low-performing but more diverse models. Thank you for your attention.